I don't know. Okay. So yeah, I'm going to be talking about evaluating the spread of climate model ensembles based on the computing platform selection. Basically, what I noticed when I was a chemistry undergraduate was that all of my lab reports had error bars on them. And when I read climate research papers, there are no error bars. So that kind of got me interested in looking into some of the error that is inherent in the climate models. And some of the error is just based on your compiler or the platform that you select to run your model. So obviously reproducibility is important, and there are changes in floating point rounding when you go from compiler to compiler or use different compiler options or get on a different system. And your answers are going to be dependent, whatever 100 or 1,000 year long run you do is going to be dependent on the selection of your compiler and your platform. So the questions that I want to answer are, what is the actual model spread due to rounding error? And is that spread dependent on the platform that you choose? So since I'm at GFDL, I ran the GFDL AM4 model, which is available on GitHub now. To simulate a rounding point error, I put a random number generator into the model and select a random point, and then perturb the model by the temperature, 1 point temperature, 10 to the minus 13 Kelvin. So it's on the level of the rounding error in the model itself. And then each ensemble point I ensure has a different point. There were a few times where I selected the same point with the random number generator and I had to throw those out. And the model is run for 1 year. So here's a list of my ensembles. Not an ensemble cast, but they are all friends. The main base ensemble that I ran runs with Intel 16. So the AM4 has a published paper, and it runs with Intel 16, the O3 option, and it runs with SSE2 vectorization. And it runs on our production supercomputer Gaia, which is a Broadwell-Haswell machine. And when we use bit-for-bit reproducibility options, it reproduces on the Broadwell and the Haswell partitions, so we use them interchangeably. And that base ensemble has 300 members to the ensemble, so it's a very large data set, probably not practical for all ensemble runs. I also ran with the AVX option, so that was another ensemble with 100 members, and I ran it with an Intel 18. We still don't have Intel 19, so I haven't run it with Intel 19 yet, but Intel 18 with the SSE and O3 options. The AVX one ran with O2, not with O3. I also ran with the Cray compiler, which is available on Gaia. So those are all on the same computing platform. They're just all different compiler options and different compilers. I was able to run on Theta. I got some time on the Theta computer, so that has a KNL platform. It does run Cray. It is a Cray, I think, but it is. I did run with Intel 16. It was available, so it's the same compiler, the same options. It's just on a different platform. And when Hera came online with Skylake, it's a Skylake machine. I was able to run a few ensembles on there in time. I only got 47, but all that was available was Intel 19. So there are some differences, but obviously it's a different compiler and a different platform. Okay, so what I did was I looked at the whole ensemble, and I took the means and I plot and compare the global means. Okay, then I do the same thing for the standard deviation. So I plot the global standard I plot the point-by-point standard deviations, and then I take a global average of those standard deviations, and I can compare that way also. So I have graphs that are just global, and then I have maps that are or that are global means, and then I have maps that are global point by point. So this is looking at the surface pressure, and so I plotted some error bars. So it's the error bars are for the base ensemble. So it's the standard deviation of the average of the global standard deviation. So all of the standard deviations around the globe. So that's what these error bars are, and they're different for each month. I used monthly mean values that come from the model diagnostics, and on a global sense, the standard deviations were all very similar. So the spread of the model on a global sense, they all follow the same kind of pattern, even with the surface pressure. And it doesn't change much going from 30 members to a 50-member ensemble to a 100-member ensemble. So I kind of, just grab 30 and then grab 50 and grab 100. Yeah, but the more ensembles you run, the tighter the spread is between the individual ensembles. So it's kind of a balance of how much computation and time do you want to spend running these ensembles when you don't get much more out of running from 30 to 100 members in a global sense. I also looked at the U-wind. So the U-wind had a larger standard deviation than the pressure. Well, the pressure is in millibars, so I guess it depends on what units you use, right? But and oh yeah, from January to this is all spin up. So this is kind of spin up of the model. That's why this value is so low. But again, all of the models all of the ensembles follow the same kind of pattern for the spread. So they're all doing essentially the same thing, even on different platforms. And then this would be, so I took the error bars off because everything was well within the error bars, but this would be what the error bars would be based on the ensemble. So the actual spreads of the spreads are kind of all over the place. And when we look at the global maps, you kind of can see that more. So this is an animation of the mean and the evolution of the mean based on the number of ensemble members. This is for the base ensemble, and it's looking at the surface pressure. And it's just a plot of the mean. And you can see that it kind of changes a little bit up here where you get more storms moving through that area. But other than that, it's pretty steady even at very few number of ensembles. So the ensemble mean doesn't really change much based on the number of ensembles that you run. So that's good. That's what you really hope for because you hope that the error isn't too big to affect this too much. This is the evolution of the standard deviation, and this does change based on the number of ensembles. So at the beginning of this loop, you see that there's some whites on there that's even off the chart. So this would be for surface pressure, so 12 hectopascals or whatever. The spread is larger than even the scale that I used. But as we get to about 30, this pattern kind of gets to be more stable. Even though the numbers fluctuate a little bit, the pattern kind of stables out, where whatever was happening over here kind of, disappears, and this uncertainty that's in the elution area, kind of the pattern steadies itself out as you add more and more ensembles. So I think about 30 ensemble members is a good way to get to the actual spread, the global spread of the model based on the standard deviation. Okay, now I have some plots of the differences in the standard deviations, and these plots don't really mean that much because it's just subtracting two numbers. There's no relative scale to these, but I figured I'd show them anyways. They are very small. The differences in the standard deviations are very small. This is for the temperature, and this is for the wind. So this is the same. So these are the K and L the K&L system minus the base, and they're both the K&L system, yes. And then I also looked at the Cray, using the Cray compiler, and I mean the values are about the same. So even though it's, the Cray compiler, remember, was on the same system as the base, so you know, we're getting kind of the same thing. This is a % difference now, so this is a little more meaningful. How much has it actually changed? So this would be the K&L minus the base divided by the base times 100. And we see like there are some hotspot areas where we see large changes in the spread, but nothing too much. For the most part, the spreads are very low. These, you know, the blue and white colors, the differences are pretty low, but you know, in the polar regions it's a little bit high, and in the Pacific also. Again, the values are similar for the Cray compiler, and I'm not really sure if this is due to the number of ensembles that you're comparing, or, you know, like if we ran 300 of the Cray, would it be closer? I'm not entirely sure, so I guess I need to do that experiment. But the values are pretty similar, where we get to the 30s, and, you know, a few spots that are 30s and 40s %, but nothing too out of control. When, okay, these are a little out of order. So for the Skylake, this one had much larger % differences, especially to the south of Africa and in the southern Atlantic Ocean over here. There's some very large values, and even in the Pacific here, very large values of the % difference. I'm not sure if that's because it's a different compiler or if it's a different system. So these are things that you have to consider when you're looking at these spreads. Is, you know, we have kind of 2 different changes in this case instead of 1 change in all of the other cases. The other thing I did was, so I compared the base ensemble to the base ensemble with just 30 members of the base ensemble. So these are the same, exact same ensembles, it's just one has less members. And again, you see that there are still some of these larger % differences, even up to 40% on the west coast of Africa here. So some of these larger values do pop up even within the same ensemble. So it could be, you know, just the number of ensembles that are selected for the comparison. All right, I flew right through this, wow. So yeah, to conclude, the ensemble means pretty much aren't platform dependent. That's what you hope, that your climate model reproduces on a different system. And in this case, at least for the GFDL model, the means don't seem to be platform dependent. The ensemble spreads over a local region are platform and compiler dependent, and you should use large ensembles to report the error due to rounding on your computing platform. These ensembles aren't that difficult to run, and you know, if you only run 30 of them, it's only 30 computational years. It's not that big of a deal if you have a large supercomputer available to you. And yeah, that's it. Thank you.